The power spectrum describes the characteristics of a time series in the frequency domain. In particular, captures the randomness that might be inherent in a random process. So the power spectrum will represent the variance or power as a function of frequency in the process and tell us where the energy is distributed. So what we want to do oftentimes is estimate the power spectrum given a set of data. And there's two main categories of methods for power spectrum estimation: parametric methods and non-parametric methods. Non-parametric spectrum estimation does not assume any particular model generated the data. And in that case, we would use Fourier methods involving the discrete Fourier transform. And if you've used the discrete Fourier transform at all, you probably have a pretty good idea of what you might try to do to estimate the power as a function of frequency. Parametric spectrum estimation techniques are based on the use of models for the data. And they assume that the data is generated in a certain way. For example, we might assume that the data is the output of a linear time invariant system with frequency response h of either j omega in response to a white noise input sequence. And this model allows us to describe many different spectral shapes because we know that the power spectrum of the output is just the power spectrum of the input, which is sigma squared, the power of the variance of the white noise, times the magnitude squared of the frequency response of the system. So by having different system behaviors in the frequency domain, we can describe different types of power spectra for X. So this is a model. It's just saying that the power spectrum is given by the magnitude squared of some frequency response for an LTI system. Now there's several different classes of systems that are typically used with this kind of approach to spectrum estimation. There's the autoregressive, or AR, which is an all-pole model. It only has poles in its frequency response. Then there's a moving average, or MA model, which would have only zeros in its frequency response. And then there's the autoregressive moving average, or ARMA system, which has both poles and zeros. And these different restrictions on whether you have poles, zeros, or both result in different classes of system models and characteristics in the spectrum estimate. Now, another example of a parametric model for power spectrum is that of sinusoids and noise. In this case, the model is to assume that the data that we measure x of n consists of a combination of capital L sinusoids with amplitudes a sub I and frequencies omega sub I plus white noise. And with this kind of a model, the power spectrum just has values of sigma I squared times delta of omega minus omega I. In other words, there's a variance of sigma I squared at frequencies omega I, and then there's a background constant level, or the white part of the spectrum, sigma W squared. And here, the unknown parameters are the powers of the amplitudes, or the variance of the amplitudes, the frequencies, and the white noise, power level or variance. If I know these parameters, then I can write down the power spectral density. So the general approach with a parametric spectrum estimator is, first of all, we observe our data, x of n. Next, we take the data and use the data to estimate the parameters of the model. For example, the autoregressive coefficients, the moving average coefficients, or the amplitude variances and the frequencies of sinusoids and the white noise level. We would estimate these parameters from the data and then get our estimated spectrum as a function of the parameters we just estimated. So, for example, in the white noise, or in the linear time invariant system model, we would have our estimated spectrum as the estimated noise variance times the estimated frequency response of the system, magnitude squared. And similarly, we do this with the sinusoids and noise model. So there's a model that underlies the data, which then gives rise to a particular form for the power spectrum. Now, the comparison between whether one uses a non-parametric method based on the DFT or a parametric method all depends on the correctness of the assumed model for the parametric method. If the model is correct when you do parametric spectrum estimation, in general, you're going to get a higher quality estimate and be able to get that estimate with significantly less data than would be required by a non-parametric method. And that's because you're exploiting the additional information that you provide when you say, I believe the spectrum has this particular form given by the model. On the other hand, if the model is wrong, let's say that you assumed the data consisted of sinusoids and noise, but actually it was a broadband colored noise spectrum, then the parametric approach can give you just wrong or even misleading estimates. So that's the risk. You can get higher performance when your model is correct, but when your model is wrong, you can get some dramatic failures. And so that's often if someone knows ahead of time, for example, that their data is generated by a resonant phenomena, then an autoregressive model might be a pretty good fit. But if you don't have a prior expectation like that, then it might be safer to use a non-parametric approach.